Here we want to graph the equation f of x equals x minus 3x to the 1/3. There are a lot of steps involved, so let's start by looking at all those steps. Okay, so let's take a look at 1 and 2 first, domain and symmetry. So we'll do those together here. Starting with domain, we look at this function. It's not quite a polynomial, right? We could rewrite this. Maybe it's a little more familiar if we rewrite it as f of x equals x minus 3 to the cubed root of x. But one way or the other, there are no x values that give us any problems here, right? We could put in 0 for x. We could put in negative numbers for x. All of those x's are acceptable, so the domain is all real numbers, which we'll write as negative infinity to infinity. Next, let's take a look at symmetry. And remember, for symmetry, we essentially plug in negative x to the function and see what we get, right? So we have two options for symmetry. We have even, f of negative x equals f of x. And we have odd, where f of negative x equals negative f of x. So we'll take our function and plug in a negative x and see what happens. Of course, it could be neither. That's a pretty common result. So here we have negative x minus 3 times cubed root of negative x. Well, since it's a cubed root, that negative comes out. So that gives us negative x plus 3 cubed root of x. Well, now we can factor a negative out to the front of this whole thing. We get negative x minus 3. Oh, sorry, this should be cubed root up here. 3 cubed root of x. But note that this is exactly our function again. This is f of x. So this whole thing is negative f of x. So that tells us that our function is indeed odd. Okay, we've completed steps 1 and 2, so now we're on to step 3, first and second derivatives. And I'll do all, let's see, so I'll do the first derivative, and in that I'll do critical points and increasing and decreasing. And then we'll come back and do the second derivative, and then in that we'll do possible inflection points and then concave up and concave down, right? So we'll do all the first derivative stuff and then all the second derivative stuff. Okay, for the first derivative step here, I'll just write that as f prime of x. And remember that our function is up here, right? F of x equals x minus 3x to the 1/3. So the derivative of that, f prime of x, then equals, well, derivative of x is 1 minus, and then we bring down the 1/3. That cancels with the 3 up here. So we have 1 minus x to the negative 2/3. Okay, so now we need to find our critical points. Those occur where either the function, or the derivative equals 0 or is not defined. And that is, of course, for x in the domain of f of x. Okay, so let's get this derivative set equal to 0 and see what happens there. So we have, let's see, 1 minus 1 over x to the 2/3 equals 0. But let's pause right here. Note that right off the bat, if this equals 0, the function's undefined. But that's one of our critical points, so we'll say x equals 0 is one of our critical points here. Okay, back to solving for x. Now we can add 1 over x to the 2/3 to both sides. We get 1 equals 1 over x to the 2/3. Multiply up by x to the 2/3. That gives us x to the 2/3 equals 1. And now you want to be a little bit careful here, because it's tempting to just take both sides to the 3/2 power and call it good. We have 1. But let's notice a subtle point here. First, if we raise both sides to the 3rd power, okay, that's simple enough. We get x squared equals 1, x squared equals 1, and then we can take the square root of both sides, but remember, when we do that, we need to tack on a plus or minus here. So it's actually x equals plus or minus 1. Plus or minus 1 for our critical points there, where the function equals 0. All right, so we will add those two up into our critical points, plus or minus 1. So these 3 critical points define 4 different regions, and we're going to test points in each of those regions to see if our function is increasing or decreasing. We call this a sign chart. At least it's commonly called a sign chart, so let's do that. Okay, so we need to test, let's see here, so we had 0 and 1 and minus 1. Okay, so now we'll pick x values inside of each one of those regions to test. So maybe we can test x equals -2 here, x equals 1/2, -1/2 in this next region, x equals 1/2 up here, and then x equals 2 in the final region. We'll test all those. Tested in what? We test them in the derivative because we're trying to figure out if the function is increasing or decreasing. Of course, positive derivative is going to be increasing, negative derivative is going to be decreasing. Okay, so let's test out these values. I like to set up a little table like this. X, and we include our derivative, f prime of x equals 1 minus 1 over x to the 2/3 power. Okay, so we'll test that out. If you don't like this 2/3 notation, you can always write this as 1 minus 1 over cubed root of x squared. It's the same thing. Okay, so let's do some testing here. We have -2, -1/2, negative, make that positive 1/2, and 2. And you may just want to type these into a calculator when you test each one of these values. So we put in -2. We don't need to know what the value is. We just need to know if it's positive or negative. So when we put in -2, we get something positive, right? Just put in -2 for x and see what you get. It's positive. When you put in -1/2, again, we're putting in for this x right here. When you put that in, you get something negative. When we put in 1/2 for x, we're at negative again, actually. And when we put in 2, we're back to positive again. And again, I urge you to check each one of those by plugging into x here and making sure you get positive, negative, negative, positive. Okay, now we can label these on our sign chart. So we have positive there, and then we're over to negative. So positive in the region from -1 to infinity, and then negative between -1 and 0. Negative again from 0 to 1, and then positive from 1 out to infinity. So what does that tell us about the function? Well, it tells us that it's increasing, and then decreasing again, and then increasing. We can write that nicely and say it's increasing on, let's see, -infinity to -1, and I'll say union 1 off to infinity. And then it's decreasing on -1 to 1. All right, so that's very useful there. We'll use that for our graph. From that, we can now deduce that we have a local maximum right here because we're going from, we're increasing and then switching to decreasing. So there's a local maximum at -1, comma, whatever the y value is. So let's clear out a little more room here. Okay, so we have a local max at -1, comma, what? Well, where do we get this second value from? It's tempting to plug -1 into the derivative, but we don't. We want to plug that into the original function. We always plug back into the original f of x. Well, it's been so long that I've lost the original function, so let's review what that was at the beginning of the problem. It was f of x originally was x minus 3x to the 1/3. So plugging in -1 gives us f of -1. Okay, -1 minus 3 times -1 to the 1/3. Well, to the 1/3 power is simply cubed root of -1. Cubed root of -1 is -1, so this gives us -1 plus 3, which is finally 2. Okay, so our local maximum is -1, comma 2. Next, our local minimum. Back to our sign chart, we see that the function is decreasing and then switching to increasing at our point here at x equals 1. So that tells us there's some kind of local minimum here at x equals 1. Okay, so we know our x value is 1, but we need our y value. Back to our original function, not the derivative, we go all the way back to the original function, plug in 1 to get that y value. Okay, 1 minus 3 times 1 is -2. So the local minimum occurs at 1, comma, -2. Okay, 2 more useful bits of information, right? We're really getting a lot of good information out of this first derivative, but that's all the information we can get out of the first derivative. So we are ready to move on to the second derivative, f double prime of x. F double prime of x. Okay, so that will just kind of label that whole section there. So with the second derivative, we'll get the possible inflection points and then examine concavity. Well, first, recall that the first derivative was f prime of x equals 1 minus x to the negative 2/3. Okay, from there we can quickly go to the second derivative, f double prime of x. Okay, derivative of 1 is 0, so that just leaves us with bringing down the negative 2/3. So we have positive 2/3 x to the negative 5/3. We're subtracting 1 there. Okay, it might be easier to rewrite this as 2 over 3 x to the 5/3. Now with the second derivative, we're looking for possible inflection points, and those occur wherever the second derivative is either 0 or not defined. So here we can see this function is not defined at x equals 0. X equals 0 gives us a 0 in the denominator, so the function is not defined. So that's our only possible inflection point. So the possible inflection point here is indeed x equals 0. And I say possible inflection point because it's only an inflection point if it's concave, if the concavity changes from one side to the other on that point. Okay, so let's set up our sine chart and check that concavity on either side of that inflection point. All right, so sine chart. Okay, same ideas for the first derivative. We have x equals 0 here, and we'll check points on either side of that. So we need to check a point in each region. In the second derivative now, so let's test x equals negative 1 for the left region and x equals 1 for the right region. Now we can set up our chart and see how those points come out. So here we have x and f double prime of x, which recall is 2 over 3x to the 5/3. Okay, and then we'll test negative 1 and 1. When we put in negative 1, we get something negative. When we put in 1, we get something positive. So we can fill in these negatives up here, and then it switches to positive. So that tells us that we are concave down from negative infinity to 0, and then concave up from 0 to infinity. So indeed, x equals 0 is an inflection point, and the only inflection point. This inflection point occurs at x equals 0, but 0 is in the domain of the function, so we can get a y value here. Recall once again that our original function was f of x equals x minus 3x to the 1/3. So when we plug in 0 here, we get a 0 back out. F of 0 equals 0. Remember, to get an actual point, we always want to plug in to our function. Now, okay, well, let's finish this out. Equals 0. Okay, let's just leave it at that. So there, we have our inflection point. That's good news. And we can also talk about our concavity. So we have concave up on 0 to infinity, and concave down on negative infinity to 0. Okay, so that's a lot of information, but we still have more information that we can get, namely asymptotes and end behavior. So let's check back in with our steps and see where we stand. Okay, so we've completed steps 3, 4, 5, and 6 to get our critical points, our inflection points, increasing, decreasing intervals, concave up, concave down intervals, and extreme values and inflection points. So now we are on to steps 7 and 8, asymptotes and end behavior, and then intercepts. Okay, so let's take a look at asymptotes and end behavior. Let's go all the way back to our original function. We keep losing it here because it scrolls off the screen, but remember our original function at the very beginning was x minus 3x to the 1/3. Okay, so there's no x's in the denominator here, so we have no asymptotes. So that's good news. Next, let's look at the end behavior. For the end behavior, we'll take the limit as x goes to infinity for the right end behavior of x minus 3x to the 1/3. And remember that the leading coefficient, or sorry, the leading term dominates this thing. So we really only need to look at the x term and not the negative 3x to the 1/3. And that's clearly going off to infinity as x goes to infinity. So our right behavior, we could say, is infinity. All right, similarly, we take the limit as x goes to negative infinity of the same function. And for the same reasons, we'll get negative infinity there. The last thing we need to do here is compute our x and y intercepts. Let's start with the x-intercepts, which means we set y equals 0. You always set the opposite variable equal to 0. Well, y is the same as f of x here. So going back to our original function, we get 0 equals x minus 3x to the 1/3. When you get to this point algebraically, it's a good practice to then factor out the smallest, I guess the rational number exponent closest to 0 or the most negative, depending upon if you have negatives or not. So here we have 1 and 1/3. So I'm going to factor out x to the 1/3. This is helpful for solving these. What's left? Well, when we factor something out, we're really dividing all the terms by it. And when we divide exponents, we subtract them. So that gives us x to the 1 minus 1/3 minus, and then we just have 3 because we factored out x to the 1/3. So really we're working with x to the 1/3 times x to the 2/3 minus 3. Okay, now we set both of these terms equal to 0 and equals 0. Well, the first one simply tells us that x equals 0. The second one is that we have to be a little more careful with. We get x to the 2/3 equals 3. We'll cube both sides. All right, cube that out, cube it out. All right, x squared equals 27. And then we take the square root. But remember, when you take the square root by your own choice, you need to tack on this plus or minus business here. So that gives us x equals plus or minus square root of 27, or 3 rad 3. But it's pretty hard to graph the point 3 rad 3. So let's do an approximate just so when we go to graph it later, we know where it is. So this is plus or minus about 5.2. Okay, so that was our x-intercepts. Not bad. We have 3 of them, 0 and plus or minus 5.2, we'll say. Then the y-intercept, there's always only one y-intercept at the most. Sometimes there's none. So to that we set x equals 0, which means we actually compute f of 0. Well, f of 0 is clearly 0. Recall that our function was this bit up here, x minus 3x to the 1/3. Plug in 0 there, you get 0. So there's our y-intercept. Y equals 0. It's our y-intercept. Okay, that's everything. Whew. Let's summarize this and then graph it. We have domain negative infinity to infinity, and that symmetry is odd, so we'll just keep that in mind for later. So when you go to graph things, you kind of sketch in the details a little bit until the graph forms. So increasing like that from negative infinity to -1, and then from -1 to 1 it's decreasing, so just right in here, and then at 1 we're back to increasing again. Okay, we have more detail with our local maximum at -1, 2, so that's way up here, and a local minimum of 1, -2, so there's our minimum. Let's go on to our intercepts down at the bottom. We have intercepts at x equals 0, and we have one at about 5.2, that's about here, and -5.2 is about here or so. Okay, then we can do our y-intercept as well. It looks like the y-intercept got left out of the summary, but it was 0, so that doesn't actually give us anything new. Anyway, sorry, y-intercept. Okay, then we have that our function is concave down from -infinity to 0, and concave up from 0 to infinity. No asymptotes, and our right end behavior goes up to infinity, and our left end behavior goes down to -infinity, so something like that. And there's all our information. Okay, our graph doesn't look too great just yet, but now we can connect everything together and see how it goes. So maybe it comes up. I don't know. You might want to plot points down here. I don't know quite what happens down there. It looks like it comes up like this, hits there, and then does a pretty sharp curve down like so. Right? And then curves back around. Try to make it odd. So I'm going to mimic what we did there. I don't know, something like that maybe. You get the idea. And then, of course, hopefully you've done this in pencil or something where you can erase all your marks and just have the graph left over. There we go. Let's compare it to Desmos and see how we did. Okay, here's the Desmos version. So yeah, we're pretty close. Pretty close. Mine went off a little steeper. So maybe if you really want to go into some detail, we could have plotted some points there to see how that end behavior really looked. But you know what? I'll take it. Ours was close enough.